Yes, hello everyone. I'm very pleased to welcome you to today's extended technical presentation on urban traffic optimization using numerical methods. My name is Hayrun Nisa Keskin, and this project has been a cornerstone of my academic journey in the numerical methods in engineering course under the guidance of Dr. Furkan Gözükara. Today, I will walk you through a comprehensive simulation based study that tackles one of the most pressing challenges in modern cities: urban traffic congestion, using a blend of mathematical modeling, algorithmic design, and software implementation. One question: why traffic optimization? Let's begin by acknowledging the core problem. Urban traffic congestion has become a defining issue of 21st century still life. Whether you're commuting to work, transporting goods, or managing urban logistics, the cost of traffic is enormous. Not just economically, but also environmentally and socially. Traditional infrastructure solutions like expanding routes or adding more signals are often expensive, slow to implement, and sometimes even counterproductive. This raises a critical question: can we manage traffic more intelligently using the data and computation already available to us? Think about it. Yes, the answer, of course, is yes. Through intelligent systems powered by numerical analysis, we can simulate, predict, and control traffic flow more efficiently. Yes, you can see my project interface. This project to build a flexible, extensible, and realistic traffic simulation system that does more than just suggest the shortest path. It uses congestion data to find the least congested, most stable, and even alternative routes, adapting in real time. We apply several numerical methods such as error analysis and floating point precision, route finding techniques, and interpolation and differentiation and solving linear systems, and LU decomposition, optimization, and ordinary differential equations, solving, and performance stability, all to solve real-world traffic challenges in a model that can easily scale from small city simulations to nationwide applications. We talk about why numerical methods. You may wonder why bring numerical methods into a traffic problem. Because traffic networks at their core are mathematical graphs, each route can be represented as an edge, each intersection as a node, and the flow of vehicles behaves much like a dynamic system governed by equations, data, and constraints. By using numerical techniques, we reduce complexity when direct solutions are impossible. We approximate behavior when data is missing. We optimize when many possible solutions exist. That's the power of numerical methods. They allow us to transform complex physical problems into solvable computational ones. Yes, here we go. Architecture overview. This system is built entirely in Python, Lagrangian libraries. Graph modeling for graph modeling, network X, and for visualization with matplotlib, and for numerical computation, NumPy and SciPy. And for the interactive interface, Streamlit. We simulate city networks like Mersin, Ankara, and the other cities. Each route is defined by, you can see, each road is defined by length in kilometers, and flow, number of vehicles, yeah, and capacity, maximum allowed traffic. Oh, under the page. Yeah. Maximum capacity. Maximum allowed traffic. Our algorithm calculates congestion using the formula. You can see. This prevents oversaturated routes from being selected by default, which mimics real human behavior. Drivers avoid jammed routes if they have a choice. Yeah. 3 main routing strategies. The system computes 3 types of routes: shortest path, and congestion aware path, and alternative path. Shortest path based purely on distance. Congestion aware path weights updated using traffic load, and this. An alternative path, not the shortest, but still acceptable if other paths are blocked or overloaded. The alternative routes logic ensures fault tolerance, which is especially useful in case of sudden events like accidents, closures, or spikes in traffic. Wait a minute. I'm drinking water. Sorry. Yes. The project is designed with the end user in mind. Through the Streamlit interface, users can choose a city and this, yeah, and choose a city like this, Ankara, and select start and end points. Was that on? Oh, sorry. Oh, selected. Yes. Select start and points and endpoints and run simulation. Then select Altındağ and end neighbor select Beypazarı. And fastest path or shortest path is the same. Altındağ to Çankaya to Yeni Mahalle to Kahramanmaraş to Ayaş and to Beypazarı. Okay, fastest route suggestions. But slow traffic detected on Altındağ, Çankaya, Altındağ, Keçiören, and Altındağ, Pursaklar, Bala, Mamak, and blah blah blah blah to Sincan. And these cities or neighbors has a slow traffic detected on. And then view real-time graphs and route suggestions, explore how different numerical methods impact results. The system isn't hard-coded to one city with just a few inputs, it can be applied to any urban environment. In our case, we demonstrate simulation for cities such as Mersin and Ankara and Hatay. The flexibility of the framework ensures it can be scaled, reused, and extended with real-time data or actual route maps in the future. And yes, this is not just a coding exercise or a theoretical model. It's a real-world prototype. It can evolve into a city-wide route planner, integrate with GPS device or navigation device, or even support autonomous visual systems, navigation map with smart route suggestion. Municipal governments could use such systems to reduce emissions, improve traffic safety, handle emergency evacuations more efficiently. To summarize, first part, urban traffic congestion is a growing crisis. Oh, sorry, this voice. Sorry, I live in dormitory. Oh, sorry. Oh, conclusion to introduction. So, to summarize this first part, urban traffic congestion is a growing crisis, and numerical methods provide scalable, flexible tools for managing that complexity. This project combines engineering, mathematics, and software to simulate and optimize traffic flow. Oh, yes. In the next section, I will walk you through the mathematical functions that power these systems, not just the theory, but how each method finds a place in a working traffic solution. Let's begin with error analysis and floating point precision. Error analysis is fundamental in numerical methods. Computers represent numbers with finite precision, which can lead to rounding and truncation errors. Understanding these errors is critical for reliable engineering and scientific computation. Practical example, suppose you are simulating traffic flow and need to some small sensor readings over time. And rounding errors can accumulate and affect the total equation. Absolute error x under 2 minus x approx. A relative error, this formula, and visualization below we show how the order of addition affects the results due to floating point error. Yes, you can see the formula in the graph. The order of addition can change the result due to floating point precision. Oh, be careful. Yes, you can see the graph as in text and the value in error analysis. Yeah. And between 0 and 5, but index 1, the value 2 points for too many numbers. And an index and getting reduced value. Index 2 and value minus 3 and index 3 and minus 9. An error analysis getting according to an error analysis graph and getting reduced values. Yes, you can see like Cumulative error in iterative addition of small numbers and getting small numbers, getting reduced. Mine type use algorithms like Kant summation for higher accuracy large sums. Yes, numerical analysis examples. An example H from selected route from Altunda to Chankaya, estimated derivative of float, and integration at 5.196. An estimated total vehicles integral from 0 to 1, hundreds of 2.17, and route finding 919.10. Lagrange interpolation at 1.5 and 1000 and 32.00. Spline interpolation at 1.5 and the same numbers. Well, you can see the time and traffic density, ODE solution order traffic density over time, and plotting our error demo A plus B plus C 131.32 blah blah 1, and in the same time and the same numbers. Stability demo unstable Euler and 9.6 and 57.6, and you can see number. Linear systems couldn't be solved, but singular matrix graphs is the same graphics, and you can see index getting reduced and value getting reduced. Time of traffic density graphs show us. Last graphic was this, and we are continuing. Yes. These mathematical tools are not abstract academic concepts, they are powerful instruments that allow us to model, simulate, and solve problems that arise in engineering and real-world systems like urban traffic. In this section, I will guide you through 12 numerical methods one by one and explain how they were practically applied in our traffic simulation project. Error analysis. Yes, let's begin with the foundation floating point numbers. Computers represent real numbers using a finite number of bits. As a result, operations like addition and subtraction are prone to tiny rounding errors. For example, adding 1e16 plus 1 minus 1e16 might give 0 instead of 1 minus this. This is a classic case of catastrophic cancellation. In our project, we handle large traffic flow numbers like vehicles per hour and small capacity difference. When computing weights repeating in loops, these rounding errors can accumulate. Solution: we use techniques and climbing Python. You will see, and the next time. A small error in h weight may cause the routing algorithm to choose or longer or incorrect paths, leading to inefficient navigation. Yeah, and you can see. Yes, let's continue. And route finding techniques. Route finding methods solve equations of the form fx equal 0. Yes, you can see. They are essential when you can't isolate variable analytically. In traffic systems, they help us compute equilibrium flows values where incoming and outgoing traffic are balanced. We use methods like bisection, yes, and Newton-Raphson, yes, and second route. And bisection slow but reliable, and Newton-Raphson fast but needs derivative, and second, good balance, yeah. Route finding is the process of finding the point where function, this formula. The most common methods are bisection, Newton-Raphson, and second. These are fundamental in engineering and science for solving equations that cannot be solved analytically. Now, route finding methods graphs. You can see. And 4 and minus 2. I will. No. Yes. Each was tested on artificial flow balance equations. We tracked their iteration counts and covariance behavior. And iterations bisection root 1.5 iterations 21. Yes, really slow but reliable. A Newton-Raphson root 1.5 results iterations 2. Absolutely fast but needs derivative. And second root the same numbers but iteration 6. Good balanced. And continuing, each was tested on artificial flow balance equations. We tracked their iteration counts and covariance behavior. And KTK, route finding is useful in future extensions of this project, for instance, when integration real-time traffic sensor data. And continue interpolation. Interpolation methods. Imagine you have traffic data for 8 p.m. for 8 o'clock a.m. and 8 half past 8 and 9 a.m. but you need the value for 8.15 a.m. Interpolation helps you estimate such missing values smoothly. 8 past 15 a.m. Interpolation helps us estimate such missing values smoothly. We implemented Lagrange polynomial interpolation and cubic spline interpolation. As you can see, graphs and data, linear, Lagrange, and spline. Interpolation estimates values between known data points. Common methods are linear, Lagrange, and spline interpolation. These are widely used in engineering, science, and data analysis. You can see this graph, interpolation methods comparison, and 0.75 peak points are, yes, these methods let us predict missing traffic values on roads without sensors and smooth out jagged flow readings. Our spline interpolation gave the best, and this spline interpolation gave the best results due to its continuity and smoothness across intervals. Yes, you can see, and that's all. And spline interpolation is generally the most accurate, the smoothest. Lagrange can oscillate. Linear is simple but less accurate. And results, you can see results. Estimate derivative of flow and 5.96 and integral from 0 to 1 102.70, and root finding is different, and 990. A Lagrange interpolation in addition, Lagrange interpolation at 1032, and the spline interpolation in the same numbers, and this graphs 100 traffic distance 100 and time 5 point, yes, index numbers on getting increase and value getting reduce. Yes. We continue. And numerical differentiation. Numerical differentiation finds the derivative of function approximately using forward, backward, and central difference methods. Accuracy improves with smaller step size, but rounding error can grow with very small steps. Affect step size on derived derivative error. Differentiation allows us to compute how fast something is changing. In our case, we used it to measure how quickly congestion is growing and rate of increase in traffic density. We applied forward difference, backward difference, central difference. You can see forward difference, backward difference, and central difference. Each method was evaluated against a known function fx equal sin x to understand its error behavior. We observed that central difference consistently outperformed the others in accuracy, especially when small step size were used. And this graphics, yes, you can see, and getting reduced this point and getting increase is central and backward difference and forward difference and getting increase, but central difference is getting reduced this point and then getting increasing. Central difference is generally more accurate. Rounding error dominates for very small h values. Step size h hash, and this number you can know, as you can know, and these graphs, ODE solutions, traffic density over time, and this, and we are still altında Tubey Pazarı, and we are continuing numerical integration. Numerical integration in traffic systems. Integration helps us compute the total cost or travel time across a route. For example, integrating congestion over time yields total delay. We applied trapezoidal rule and Simpson's rule and Skypice quad for adaptive integration. This helped in estimating vehicle totals over a segment, comparing cumulative delay between different paths. Simpson's rule was most accurate for smooth curves, while quad was best for irregular real-world data. And numerical integration finds the area under a function using trapezoids in Simpson and quad adaptive methods. Accuracy and applicability vary. As you can see, number and 0.8 and Simpson again 0.8 and quad error estimate at 9.8, and this node quad is generally the most accurate. The Simpson and trapezoid are fast and easy. An integral area, the graphs, and you can see in these graphs numerical integration is used, for example, to calculate total distance or energy from sensor data. In this area, this shows me totally, and again, yes, with solving linear systems, traffic flow distributions, linear systems, and solving linear systems traffic flow distributions form a network of traffic flow distributions form a network of equations. If you know flow into A and flow out of B, but not the intermediate flow at C, you can set up equations AX equal B. We solve such systems using NumPy and .linolog.solve for direct solution, custom Yakov iteration for sparse systems. This made the system scalable, especially when modeling larger networks with many unknowns. And we are reading Linear systems of equations are fundamental in engineering and science. They can be solved directly, etc., using NumPy, linear solve, yes, and iteratively, yes. Direct methods are fast for small medium systems. Iterative methods are preferred for large or sparse systems. And direct solutions. Direct solution NumPy.linear, and this number is 0.5 and 1 point and 0.5 again. Jacob iterative solution, and again numbers, but iterations 61 is different. Direct methods are fast and accurate. Iterative methods are better for large or sparse systems. And linear system solutions graphs, as you can see. Oh, and direct and Jacobi. Yes, as you can see, the graphs and the same numbers, because we are the same steps. And continue. And next, LU decomposition. When solving multiple systems with the same coefficient matrix, such as rate congestion calculation, LU decomposition becomes efficient. It splits the matrix into lower L, upper U. Once decomposed, you can use L and U for many right and right-hand side vectors. And we used Python from SPI-C. Oh, sorry, SciPy. But that's line lake import, LU factor, and LU solve. Result: the competition time reduced by over 60%. 60% in batch simulations. Sorry, I'll drinking water. Yes. LU decomposition factors matrix into lower and upper triangular matrices. This is useful for solving multiple linear systems with the same coefficient matrix but different right-hand sides. And solution for B1 at the same numbers, 0.5, 1, and 0, again 0.5. But solution for B2, 0.3, and at the same time 0.8, and the same time minus 0 point and 0.4545. LU decomposition is efficient when solving AX equal B for many different B vectors. You can see, as you can see. Yes. Sphere optimization. Optimization techniques. At its core, route selection is an optimization problem. Minimize travel time or congestion under capacity constraints. We use greedy algorithms to select best paths. SciPy.optimize.minimize scalar to find cost minimizing thresholds. A sample cost function might be Python cost acute travel time plus penalty factor plus condition level. Yes. We minimized this for different path configurations, and the result was smarter route choices compared to naive shortest path algorithms. Yes. We are writing optimization techniques. Optimization finds the minimum or maximum of a function. Here we use SciPy's minimize scalars. Yes. As I can minimize scalar and minimize for scalar and multivariable problems, and is important for multivariable problems. Scalar optimization results x equal 2.00 fx equal 1.00. Okay, that's right. Multivariable optimization result x equal 0.999 and 0.999. Oh, and this numbers is different and is less than number fx and 0.00. And this important point minimize scalars for 1D problems, minimizes for multi-dimensional problems. Optimization is used in engineering, economics, and machine learning. And it's important. It's so important. Machine learning, optimization, so important. And again continuing ODE solving. ODE solving ordinary differential equations. ODS calls. While the current simulation is static, traffic is inherently dynamic. Vehicles enter, move, and exit. We modeled future versions used ODEs and frac dq and dt equal fq point t. Using SciPy integrate solve EVP with RK 45 and RK 23 solvers. And this allows us to predict traffic build up during peak hours, simulate evacuation or construction based bottlenecks. And as you can see, ODE solving. ODEs models dynamic systems. We solve dy with dt eq minus 2y using SciPy solve IVP with different solvers and compare them. And RK 45 final value is 0.0184 and RK 23 final value and 0.0181, and all these solution comparison and graphs. And as you can see, RK 45 and RK 23 and analytical, and getting reduce and values and getting reduce is the time. RK 45 is more accurate for stiff problems. RK 23 is faster for simple ones. As you can see, this allows us to predict traffic building during peak hours, simulate evacuations or construction based bottlenecks. Yes. In performance analysis and numerical stability. I'm sorry. Okay, let's try it. Performance metrics are vital. We measured time to compute routes and memory usage per t-graph, algorithm response to sudden input changes. Example, shortest path time and 5.6 ms and congestion aware path and 9.8 ms, an alternative fallback route in 11.2 ms. We benchmarked small, medium, and large networks to assess scalability. And performance analysis measures speed and stability checks. If small errors grow, here we compare timing and show numerically unstable recurrence. Oh, sorry. And mp.sum and 0.000375 as manual sum and 0. And these numbers as you can see graphs uh, compare timing and show numerically and index in getting increases and value is getting increases. Analysis is that's true and measure speed and stability checks. Yes. And unstable recursion can lead to overflow or meaningless results. Use stable algorithms when possible. Yes, and this you know that. So you know. And let's pass visualization and documentation and all this that's like this visualization and documentation and graphs are essential for understanding system behavior. And we are using MATLAB for plotting, Streamlit for UI, and Graphviz for flowcharts. We documented every function with inline commands and exported charts to explain congestion hotspots, solver accuracy, route difference. These visual aids made the simulation both interpretable and publishable. Yes, good visualization and this writing. Good visualization and documentation make numerical methods understandable. Here's a flow chart for route finding algorithm. And a comparative analysis is not, I think it's isn't it. And lastly, we compared all numerical methods side by side. Each method was evaluated for accuracy, speed, and stability and suitability for traffic modeling. We compiled a table mapping methods to their use cases, strengths, and trade-offs. This analysis is what transforms the project from a tool, a framework ready to be adopted and improved and extended. And in summary, oh sorry. In summary, these 12 numerical methods form the computational backbone of our traffic optimization system. In the next part of the presentation, I will demonstrate how we applied these methods to realistic traffic scenarios using multiple cities and varying conditions from free-flowing traffic to road closures. Let's now explore the simulation results and understand how these algorithms perform under pressures. Yes, and let's try and the other cities and maybe Hatay. Okay, or all of cities of Turkey, and there are sorry. or Mersin. Mersin. For example, we will go to from Yenişehir to Silifke. Yes, fastest path or shortest path is the same. Route suggestions: Yenişehir to Mezitli to Erdemli to Silifke. As you can see. Or the other neighborhood, Bozyazı to Mezitli and Aydıncık, Silifke, Erdemli, Mezitli. That's true. Or Akdeniz or Tarsus or Yenişehir. And in the same time, Mezitli, Yenişehir. And the same time, slow traffic detected on and Yenişehir to Mezitli, Tarsus to Akdeniz, Tarsus to Toroslar, Erdemli to Mut, Erdemli to Mezitli, and all the neighborhood of Mersin. And the slow traffic detected on, we will show you. We will show it. Now, each scenario is designed to test a different accept for urban traffic flow from normal operation to extreme congestion and road closures. And scenario 1 baseline no congestion. Let's start with the most basic case, the baseline scenario. Here all routes in the selected steel, let's say Mersin, operate far below their maximum traffic capacity, and this slow traffic is the same name. And we initialize the graph with flow values on all edges, and these edges. In other words, every route is underutilized. Observation: when we run the simulation, short path or fast path, and the congestion aware path, and again, and the alternative path is not triggered because there is no need to reroute. Results: this confirms that the algorithm behaves normally under low stress conditions. There is no performance penalty, no unnecessary rerouting, and the output is optimal. Yes, and scenario 2, localized congestion. Let's stimulate our more realistic situation. What happens is if the other news are in Hatay or Ankara or Hatay, and it's changing interpolation and spline pollution and changing numbers and changing integral and root finding, numerical differentiation, and everything is changing. Anyway, we select the critical edge in the graph. Perhaps the connection between İskenderun and Antakya, and artificially increases the flow value close the capacity. At the same time, observation The algorithm still picks the fastest path, picks the same route but blindly. However, the aware path and detects the high flow reroutes accordingly, and logic is triggered since the primary route is no longer efficient. Result: the reroute path is longer in distance but shorter in travel time because it avoids the saturated route. This showcases the power of adaptive routing based on real-time data. And as you can see, oh sorry. And finally, let's simulate a road closure. One of the routes included in the optimal route is removed entirely from the graph, mimicking a sudden closure due to maintenance or as accident. The system detects that the original shortest path or fastest path is invalid and immediately takes over, but there is no crash, no delay, and no manual intervention. Alternative path immediately takes over. Result: it confirms the system's fault tolerance. It adapts not only to slowdowns but also to structural change in the road network. This is particularly important in disaster response or emergency evacuation planning. As you can see, our congestion aware path is active in all stress scenarios, and the alternative path is successfully. Adaptably, from insights from simulations from these results, several key insights emerge. Adaptably, the algorithm dynamically shifts traffic based on conditions. No manual tuning is required, and flexibility. The system performs well across different layouts, congestion patterns, and failure scenarios, and intelligence. Unlike static routing, this system thinks like a human would, avoiding traffic, rerouting logically, and seeking alternatives. Oh, and this quote. Now that we have discussed how the system was designed and tested under various simulation and condition, let's turn our focus how well the system performs in practice. In engineering, it is not enough to have a theoretically sound algorithm. And then ah, like this. In engineering, isn't enough to have theoretically sound algorithm. It must also be fast enough to serve users in real time, stable across varying inputs, and scalable to handle feature expansion. In this section, I will walk you through the system's performance in four areas: computation time, adaptability, route stability, and scalability. And we will look our codes. As expected, The congestion-aware path takes twice as long as the short path. The urban traffic flow simulation in the layout wide and Streamlit as ST traffic network and from simulation and traffic networks and Turkey cities and all of Turkey cities and districts, all of Turkey cities and districts and generate them in network. And from visualization, import plot traffic network. And from optimization, import find best route, find least congested route, and find alternative route. From interpolation, import Lagrange interpolate, spline interpolate, and import NumPy as NP. Import random and import MATLAB pyplot as PLT. And these libraries and here's requirements. And set up Streamlit page configuration and these codes and st.set page config page title urban traffic flow simulation and layout equal white and st title urban traffic simulation and route suggestion is different names. Yes. And city selection sidebar and choose from all Turkish cities and this selections and the sidebar, sorry, and generate index Mersin if Mersin Turkish cities as and generate or load the city traffic network nodes, discrete age routes and network data and we will use and we was use to network data generate them network and tn traffic network and tn dot set random flows and assign random traffic flows to age to calculate travel times for each it's based on flow and capacity, get age, speeds, and identifies lost age for visualization. Speeds equal tiny dots. Get age speeds, slope age, against lost age. And then get list of nodes, districts for the selected city. Nodes and for and in tn.g nodes and col1 and col2 and columns and with call with subheader route selection and route selection default start and end indices for major cities and this and route selection this. And then set default start and indices for major cities start index and end index and 0 or 5 or for 1 if city Mersin and Mezitli in nodes and Tarsus in nodes. Start index Ankara again and Elif City Ankara and Çankaya in nodes and Keçiören in nodes and selected models. Start index Hatay and İskenderun in Antakya in nodes. Start index and end index nodes dots index İskenderun Antakya. User select start and end districts and this start neighborhood and end neighborhood and this start neighborhood and end neighborhood and then find the fastest route using travel time as white and time find the best route shortest path and this shortest path and fastest path, and the same. Alternative path, alternative route, find the alternative routes. Route suggestion, fastest, and fastest path, no path found, slow traffic detected on, and this slow traffic detected on, and these discretes. And all routes are flowing smoothly. Recommended alternative route. Oh, recommended alternative route. Yes, this. Always show a route description below. Alternative path and alternative path shortest path. Yeah, a leaf, alternative path equal shortest path, or alternative path and least alternative path and least shortest path. The alternative route is identical to the fastest route. st.markdown and route, and join shortest path. And then no alternative route found, st.markdown route shortest path. And else, error, no alternative route found, no route available. And this, no alternative route found, route Antakya, because it's the same, yeah. But route Antakya to Altınözü. And navigation map, column 2, this navigation map, and the column parameter has been depressed and will remote in the future. And visualize the traffic network, highlights low weights and bold the selected and alternative routes. Plot traffic networks T.T.N.G, speed, slow weight, path, shortest path, alt path, alternative path, T equals T. And then continue, markdown is null. Application of numerical methods. And numerical methods tabs, and each tab demonstrates a different numerical methods with real data visualization. And error analysis, route finding, and this. Route finding, interpolation, numerical differentiation, and all of them. Comparative to comparative analysis. And create Streamlit tabs for each numerical method. Method tabs for error analysis, route finding, interpolation, numerical differentiation, numerical integration, linear systems, LU decomposition, optimization, ODE stalling, performance, stability, visualization and documentation, and comparative analysis. And error analysis, explain the importance of error analysis in numerical computation, and this verse and these explanations, this error analysis is fundamental as numerical methods, the same words, and the finite numbers with precision, okay, rounding, which can lead to rounding, yes, it's the same word. Yes. Practical example. Suppose your simulation. And practical example. And these formulas. An equation, absolute error and relative error, And below we show how the order of addition affects the results due to floating point error. Demonstrate floating point error with large and small numbers. And as you can know, and this form leads st that's right fa plus b plus c, result 1 and result 2, and this result visualize cumulative error in iterative addition. And this iterative iterative and markdown and st dot subheader numerical analysis example. And numerical analysis dynamic drive, dynamic flow, and estimate total vehicles and equilibrium flow, routing, and flows. And route finding, interpolation, ODE, floating point, error, ABCE flow, stability, stability for flow, and try accept an example function or bisection. Route finding. It's route finding. Is the process of finding. Yes. Or bisection. Bisection formulas and FAB tool equal 1e minus 6 max iteration 100. And default bisection methods, but return none. For I in range max iteration a plus b plus 2. And these formulas and Newton-Raphson default in Newton dff df x0 total eq 1e minus 6 max iteration again 100 x equal x0 for I in range max iteration. And these formulas and scant f x0 x1 tool eq1 e minus 6 max iteration equal 100 for I in range max iteration f0 and f1 f equal fx0 and fx1. And these formulas, secant formulas, and root bits, it bits bisection AB and root Newton, FDF x0 and root secant and FAB again. And you know these iterations and these roots. Yes. My battery. Yes, we'll continue plots and the sex titled our set title and set X label, set Y label, legend PyPilot. Info section is RAPS, is robust and Newton-Raphson is fast but needs derivative. Second is good compromise. And then interpolation, we are the interpolation. And yes, this interpolation methods, comparison, and this writing, and Lagrange and cubic spline, and these formulas, and Paul y, Lagrange x y, x tens or y, and spline x pilot dense linear Lagrange, and this interpolation methods, comparison, and spline interpolation is generally the most accurate, smoothest, Lagrange can oscillate. Linear is simple but less accurate. And numerical differentiation. And numerical differentiation, and for h in h values, fx0 plus h minus fx0. fx0 derive and true derive fy, yes, full name, main FVD and BVD in can and BVD errors, and these errors h in values and ax dot log h values and VVD errors and label VVD acute forward difference and BVD backward difference and CEN and central difference and step size h in this for and graph. Forward graph and error effect of step size and derivative error and SkyPy integrate import quad sims, and this numerical integration and this section numerical integration. General purpose integration of vector valued functions and general purpose double integration, general purpose triple integration, and general purpose ND integration. And NQuad. And cluster vector quantization and physical and mathematical constant and units dataset methods and FFT equal discrete Fourier transforms and FFT pack and legacy discrete Fourier transforms and integrate integration routines. Yes, and quad sims and trapezoid. And in trapezoid, integrate along the given axis using the composite trapezoid rule. If x is provided, the integration happens sequence along its elements. They are not sorted. And integrate y plus x along each one first slice on the given axis. Compute int y and x and dx when x is specified specified. This integrates along the parametric curve, computing and parameters and y array like input array to integrate and x array like an optional the sample points corresponding to the y values. If x is none, the sample points are assumed to be evenly spaced dx apart. The default is none. The x scalar optional. The spacing between sample points when x is none, the default is 1. X is equal in optional, the axis along which to integrate. Yes, like this. We are continuing anthropoid in these formulas and Simpson and these formulas and quad and these formulas. And iteration is 6f. All the Trapp's values and Simpson values and quad values 6f and fast and easy trapezoid are you can use every time and plots and discuss and method types and linear systems. And linear systems is you can see and direct solution and Jacob iterative solution and discuss an explanation direct solution A equal and B equal and MP array and R array list and D type plot actually definitely and iterative Jacob iterative solution AB and x0 equal 1 and draw 1 e minus x minus 8 sorry and zeros like b if x0 is none as x0 dot copy yes. And MP0 is like D type like order and ND array and default zeros like is the same with the bool and the shape like and all of them none. And continues and Jacob iteration and explanation. Direct methods are fast and accurate. Iterative methods are better for large or sparse systems. And visualization. And visualization is 3 values and with linear system solutions. And again, in the visualization page, we will show you. And then finally we are LU decomposition. LU decomposition is different numbers using. Okay. From SciPy.line import LU factor, LU solve. This explanation compute pivoted LU composition of a matrix. The decomposition is A equal P L LU. Where P is a permutation matrix, L lower triangular with unit diagonal elements, and U upper triangular parameters. Equal MN array like matrix to decompose, override a bool optional whether to overwrite data may increase performance, and check finite bool optional whether to check that the input matrix contains only finite numbers. The same link may give a performance gain, but may result in problems. NMP array. Built-in mutable sequence. If no argument is given, the constructor creates a new empty list. The argument must be iterable if specified. Then continues. LU decomposition is efficient when solving AX equal B for many different B vectors. Optimization techniques. Scalar optimization results. And multivariable example. And we are using 3 variable or multivariable, and it doesn't worry. It doesn't matter. Where is multi? Minimize. Minimize where X is a 1D array with shape and n args the tuple of the fixed parameters needed to completely specify the function x0 and nd array and shape and initial guess. Array of real elements of size where n is the number of independent variables. Tuple optional extra arguments passed to the objective function and its derivative, and fun, jack, and has functions. Methods, set str or callable optional type of solver shall be 10. Non-dermite and see her optimize that minimize non-dermite, and Powell see her optimize that minimize Powell. And let's again continue with methods types and scalar example and SciPy integrate. But ODE is solving ordinary differential equations. And this RQ45. ODE's model dynamic system we solve in these formulas, and from SciPy integrates import solve an IVP, an ODE function, and RQ function, and 45 and 23 label is the streaming st. Now streamlit. Right, and app in some important in performance analysis and numerical stability. And this performance analysis and numerical stability is timing example mp.random 100 or 0000, and this stability example and timing example, and these formulas. These codes unstable recurrence can lead the overflow of the meaning results. Use stable algorithms when possible. And with method types and visualization and documentation. And this course and this writing and diagram, this check roots, update interval, check compute midpoint, and check FA and FB and turn the 0, and choose interval A and B since start, and AB and BC and CD and DE and EF, and AG flowchart, and this all of them flowchart. And if A and G is yes, and H and flowchart, graphics chart. Flowcharts and comments help document and algorithms for others. And the last comparative, 12th comparative analysis and case study, and and is now, and root finding methods part. And we compare bisection, Newton, Robson, and second methods on the function, and this all which is faster and easily, and these all of them bisection and Newton and scant make them comprehend linear. And from SciPy interpolates and Lagrange cubic spline, and this in linear interpolation comparison, this codes spline is generally, and this codes interpolation comparison, spline interpolation, and the Simpsons quads in these algorithms. And ODE solver comparison, and both solvers are accurate. And for this simple problem, but our key 45 is generally more stable for stiff equations. And in the NPI, and that's for an NP random, and Jacobi algorithms iterations, and iteration, max iteration and time, and Jacobi. It's NumPy explanations, model NumPy. We were using NumPy libraries and model NumPy, an array object of arbitrary homogeneous items, fast mathematical operations over arrays, linear algebra, Fourier transforms, and random number generation. And how to use documentation. Documentation is available through forms and docstream provided with the codes, and you can see instance, an ABC instance, absolute, calculate the absolute value elements wise, and parameters are X array like input array, out, ND array, and none, and ABC, and errors, writings, and analytic sum, and total time analytical, and numerical trapezoid, and and root length, analytical total travel time, and trapezoid numerical total travel time. And for discrete data, and numerical and analytical results are nearly identical. And no root selected. And summary table, method strength and weakness, and these methods, and Lagrange, sprint, and all of them. Bisection, Newton, second, linear interp, and Lagrange and spline and trapezoid and Simpson and quad and direct sol, Jacobi, Archie 45 and Archie 23, all of them. And robust always converse and fast quadratic converse and no derivative needed fast, simple fast, and uses all points. Smooth, uh, accurate, fast, easy, accurate for smooth data, adaptive, very accurate, good for large space system, accurate for fast for small systems, and stable, accurate, and fast for simple problems. And weakness, slow, needs break rating, needs derivative can diverge, needs two gases can't fail, and low accuracy can oscillate, needs more computation, low accuracy for raw data, needs even intervals, so slower for simple cases, not for huge sparse systems, slow for small systems, more computation, less stable for stiff problems. And finally, summary, comparative analysis helps you choose the right method for your problem, balancing speed, accuracy, and robustness. And it was our main.py. And this sample network JSON. And this is discrete Istanbul, for example Ankara, for example Mersin, for example visualization codes, and these libraries imports, and elif, and for example Mersin, and for example Ankara, for example Hatay, and these edge colors, root edges and root appendant, and this in the navigation map, and this edge is the from code. Sorry. And legend force, as you can see, and the legend handles orange, red, green. Yes, that's all. And traffic network, and again this T's or discretes, and we was using network as X and JSON and NumPy, SkyPy, and integrate, optimize, and MISC derivative, and generate them networks in Mersin and Turkey districts, and Mersin, Ankara, Istanbul, İzmir, Bursa, Hatay in big cities. And these kilometers or south, west, north, far southeast edges. And these codes raise value in either JSON paddle or the smallest states. And the capacity in the seed or this code set random flows. And MP random seed, and this goes and kilometer max speed, get edge speeds, and calculate traverse times, and get slowest edges, and estimate derivative self age, and estimate total vehicle age, and find equilibrium flow age, Time spent, value spent, and stability the most in floating point error. And this, you know, uh, we're using Streamlit Run app and traffic simulation. No, I can I can tell you. I was telling you, and this visualization and sample action and readme my readme desk file. And yes, in conclusion, in conclusion, this project simulates urban traffic flow using numerical methods and provides real-time suggestions for alternative routes based on traffic conditions. The project covers all the required topics of the course, including errors analysis and route finding and interpolation, numerical differentiation and integration, and linear systems, and LU decomposition, optimization, ODE solutions, and performance analysis and visualization. The simulation models a route network and computes traffic density and speed on each route segment, and the user interface allows users to select start endpoints, visual traffic, and receive route suggestions. All algorithms and methods are explained in the project report and video. And thank you for listening to me. I hope so. Uh, you will understanding. I hope I could explain. Thank you. Thank you for everything.